So now we want to look at how to determine which side of a reaction will be favored in an equilibrium when you're reacting an acid and a base together. To do this, what we need to do is we need to be able to compare apples to apples. So what we need to do is we need to compare the acids from each side of the equilibrium and compare those pKa's. Or we'll look at how to do that without pKa's in just a minute. So when acids and bases react, they're going to lead to equilibriums or something that we consider to be more of a complete reaction in one direction or the other. And so we can predict what that equilibrium is going to favor by looking at the pKa's. So pKa's is important there. Now, we are going to favor the reaction side with the weaker acid. So the one with the lower pKa is more reactive. It's a stronger acid. And so that is the one that is going to react most, and so we can push the reaction then to the other side, and we know which side that is. If there's a large disparity in the pKa's, that means that basically we're going to go to a completion situation and not just an equilibrium situation. So here's an example. So we've got this acid, its pKa is 4.75. We're just going to use this with water, and we can show how that reaction takes place to give us H3O plus, as well as the conjugate base for the acid. Well, when we're comparing the pKa's, we have to compare the pKa's of the two different acids. So this pKa is negative 1.74. What that means is that this pKa is significantly smaller. So what that means is that when we're looking at which direction this equilibrium will go, it is going to favor that side much more than that way. And that's because your pKa is negative 1.74. Okay, so that's how we look at things for different reactions with pKa's. So what about if you don't have a pKa chart on you? You can still be a good chemist. So there's ways to predict the relative stabilities of the pKa, and that will help us determine what's going on with reaction. Okay, first thing to understand here, and we sort of talked about that in the last video, when you have a strong acid, it's going to have a weaker, which means that it's more stable, conjugate base. I don't know if you all have realized this when it comes to nature. The world doesn't like really strong things. We try to get things that are kind of towards the middle. And so that's what's happening when our strong reactions happen with a stronger acid and giving you a weaker conjugate base. That's sort of what things are going towards. That also means that weaker acid have stronger conjugate bases. So you got to be careful with that too. But if you have two acids that are reacting, the reaction will favor the side with the most stable conjugate base. So let's look at what is going to stabilize a base. When we're comparing two atoms with a negative charge in the same row of the periodic table, the most electronegative atom should have the negative charge, right? So if you have NH2 minus versus OH minus, where this oxygen is going to have a negative charge on it, that means it's more stable because oxygen is more electronegative. In a similar way, we can look at things that are in the same column of the periodic table, and those that are larger, having a negative charge is more stable. So these two things sort of go hand in hand with this. That means that Br is going to be more stable with a negative charge on it than Cl minus. Okay, so that's rule number one. That's the thing that tops everything else. So I'm doing this in order. Next comes something that we have already worked on, and that is resonance. And resonance is the answer to so many different things too, but resonance stabilizes charge. If everything in rule number 1 is equally applied, then the structure that has more resonant structures to it will end up being more stable as a conjugate base. So here's what that means. So if we look at this guy right here versus, let's say, this guy, and he has multiple resonant structures, that means that as a base, he is more stable. What that also means is that this guy, as the acid, which would be the conjugate acid of that conjugate base, is going to be more acidic than this one. Why? Because the conjugate base of this will be resonance stabilized. Both of them will have a negative charge on an oxygen. But if you have more possible resonance structures, it will stabilize that molecule. Okay, next. Again, not as important as resonance, so this is the next thing down the line, is inductive effects. Inductive effects basically means you're pulling a negative charge or positive one over a distance, okay? So we have 2 examples here. So here we've got a carbon that has 2 fluorines attached to it, and that same carbon has an O- attached, versus not having those fluorines present with the same O-. Well, fluorine is electronegative. It's pulling electrons towards it. So the mere fact that you've got fluorines pulling electrons towards this end of the molecule, right? They're being pulled back towards that direction. It will help stabilize that negative charge on the oxygen, okay? And finally, we have hybridization. So hybridization is the last thing in these, but it still is there. So sp orbitals are more s character than sp3. So they're kind of shorter, they're a little bit, thicker. And so in general, what that means is that negative charges are stabilized more so in sp orbitals than they would be in sp3. So sp2 is obviously in the middle. And so what that means is that the H right here is going to be more acidic than one of the hydrogens right there. Okay, so yeah, you just basically go through those rules, and the first one you get to where there's a change, that's the one will just tell you which one has the most stable conjugate base and therefore is the most acidic acid. So next we need to also look at what happens when we have cation stability to consider. We kind of go through the same types of things. And yeah, you want to compare most of the time the charged species. And remember that reactions will favor the weakest acid. So a lot of these things are kind of just going to be reversed. So first we look for the most stable atom to hold the charge. Well, don't put the negative, or just the same way that you don't put the negative charge on something that's not electronegative, you don't want to put a positive charge on something that is very electronegative. So if we're comparing these two things with a positive charge on them, well, oxygen's more electronegative, so it doesn't want to have that positive charge, which means that this is more stable. And therefore, if this is more stable, it will be less acidic, right? Because it can hold that positive charge more easily. This guy wants to get rid of it. Same way we were looking at before, the size of the atom makes a difference. We see here that sulfur has a pKa of minus 4.4, so it's a stronger acid than that of oxygen. So S can take the electrons more easily, but cannot hold the positive charge as easily. So again, the opposite is applied. When it comes to resonance, we need to often compare the stability of the conjugate base to assess these. So sometimes we go ahead and remove that hydrogen and then look at what we have remaining. So in this case, our conjugate base is resonance stabilized, versus in this case, it is not. If the conjugate is resonance stabilized, where this one is not, then it's the strongest acid because it's a weaker conjugate base. It's a not as stable conjugate base. We typically see that inductive and hybridization effects looked more with the negative charges, not the positive. So that's sort of what we tend to see most often right there. Now you do have to be careful with some of this stuff as you go to do your reactions in general. So let's think about this example here. We've got a pretty strong base that is reacting with water. And when it reacts with water, we can see that the pKa of the conjugate acid is pretty high. So if we're going to favor the side that has the weaker acid, which would favor this side, you have to be careful. If you were to put these together, then what's going to end up happening is that instead of getting this as your base, you're actually making the hydronium ion. So you don't have as strong of a base as what you think you will. That is something called the leveling effect, and we need to make sure that we don't use water in a case like this. So that's partially why we avoid water as an organic solvent or in our reactions in a lot of cases. So that's something to consider. Other things to consider. We have to know that sterically hindered ions can be subject to solvent effects. So as the solvents may not as readily stabilize those charges just because of steric hindrance. So there's not as many areas for the solvent to sort of solvate something. Counterions are present if or if not written. So that's something to be aware of, okay? And then we haven't talked much about Lewis acids, but Lewis acids include metals, and those are things that we often use in catalysts. So we're going to look at that as we move forward, okay? Thank you. Practice this stuff. Okay, let me know if you have any questions.